Hello, and welcome to this introductory video on combining resistors. In an earlier video, particularly the one about resistivity, we discussed that if you wanted to sort of tailor the resistance of some object, then you could look at its resistivity, its length, and its area, for instance, and then set up whatever resistance you needed. But suppose you wanted to do that in another way, which is namely combining resistors. So you have already two existing resistors. What sort of results can you get for the effective resistance if you combine them in different ways? So let's think about this a little bit. We really have two choices for what we're going to do if we have two resistors. So we've got a resistor, say R1, and a resistor R2, and they've got resistances R1 and R2. What can we do with them? Well, there's two choices for how we're going to connect these things. I can connect them basically. So I'm going to put a battery. I'm going to connect it. I could do this in order to connect two resistors to the battery, or I could do something not quite the same, but maybe I would put just R1 there and R2 there. All right, so I have two choices, and you probably recognize this. This is a parallel circuit, and this is a series circuit. Series because they're one after the other, they're chained together in a series, and parallel because the current can flow parallel down either path and then get back to the battery. All right, so let's see what effective resistance these two combinations result in. The way we're going to do that is, of course, we're imagining, basically, in this question of effective resistance, suppose we were to replace this combination in parallel, so this whole part of the circuit, if I replace that with a single resistance, then that would have some effective resistance. And if I replace this part of the circuit, I don't know how to draw it, a whole section with a single resistor, then what resistance would that have? All right, so that's what we're trying to do. Then both of these would look like a battery and a single resistor, and a battery and a single resistor. So that would obey V equals IR effective. So if R effective is the replacement of these guys. Now, in order to figure out what R effective is, we need to think carefully about some other equations we could write to describe these things. So let's talk about the series case first. If we're looking at the series case, then what is true? Well, whatever current is flowing through the effective resistor along this wire is also the current that flows through just that resistor, because there really only is the one wire. So this resistor, and the effective one all share the same current. So in the case of series, I can write down that V is equal to I can write down that V1, whatever energy loss or potential difference I suffer in crossing R1, is I times R1. And I know that V2 is I R2. And I know that by the time I get around, I've got to have gotten rid of all of V. So I know that V is V1 plus V2. All right, so let's take a look at this. We have V is V1 plus V2, which is supposed to be that V. So let's work with this. V then is I R1 plus I R2. I can factor out the I. So then it's just R1 plus R2. And that's, of course, equal to V. And then I just compare. In my series case, V is I R1 plus R2. It's supposed to be I R effective. So in series, R effective is just the sum of the individual resistances. So how are we going to do this for parallel? Well, let's make some space. And let's just record our result. R effective in series is R1 plus R2. Oops. Put that back while I erase. So what are we going to do for the parallel case? Well, we have to think carefully, what is it that they share? In the case of this parallel circuit, the current actually branches. It splits here. Some of it goes down this path and some of it goes down this path. So it is not the case that we can talk about the same I. However, recalling stuff about equipotentials and things like that, we know that before we encounter any resistance, we've got a potential of V up here. All along this top wire, it's all still V. It's connected. It's at V. We drop our potential as we cross the resistances. We lose some energy in overcoming this resistance. And so down here, we get back to our V is 0 down there. So the potential difference across R1 and R2 is going to be the same this time. So in the parallel case, we can go ahead and look at that. So we know that V is equal to I1, whatever the current is going along this branch, times R1. And we know that V is also equal to I2, R2. They're both separately ohmic. They've got a total potential difference of V, and there's some current I1 flowing through here and some current I2 flowing through there. But of course, over here, they're together. So the total current that I was looking at going into my effective resistor is just I1 plus I2. So let's go ahead and put that to use. Since we're now interested in trying to match currents, we're going to rearrange these things. So rearranging the top one, I can get that I is equal to V on R effective. Here I can get I1 is equal to V on R1. And I can get from here that I2 is V on R2. So then I can form I, which is I1 plus I2. I is I1 plus I2 is V on R1 plus V on R2. And then I can go ahead and factor out the V. So that is equal to V, is equal to, so that is equal to V 1 on R1 plus 1 on R2. Okay, but that looks a lot like this if I make the identification that 1 on R effective is 1 on R1 plus 1 on R2. All right, and so that is our relationship, and I can add one little bit to make it slightly more succinct. That is really saying that R effective to the minus 1 is equal to all of that stuff. Or I can shift the minus 1. So instead of putting it there, I can put it on the other side of things. Certainly true that that R effective is 1 on R effective, but I can just put the minus 1 there. So R effective is this combination of the individual resistors.